Hello everyone, my name is Zhao Zhang. I'm from East China Normal University. I'm very happy to present our paper, Provably Tightest Linear Approximation for Robustness Verification of Sigmoid-like Neural Networks. Acting as classifiers, neural networks have been adopted in a variety of applications, such as pattern recognition, image understanding. It is a growing trend that embedding them in safety-critical systems, such as self-driving, to make judgments like human experts. However, neural networks are found to be vulnerable against robustness and may suffer from adversarial attacks and environmental perturbation. For example, a Tesla car in autopilot mode caused a fatal crash as it failed to detect a white trunk against a bright sky with white clouds. Because applications in safety-critical domains demand high reliability greetings, it is necessary to formally certify the related properties of neural networks. Among them, robustness is one of the most important properties, which requires neural networks to make the same classification for all perturbed inputs in a reasonable perturbation range. We consider an example to explain how a perturbed image is classified. As shown in the figure, a normal image of a dog can be correctly classified by a neural network. We assume that the image can be perturbed within a 0.05 distance and L infinity norm. There exists a perturbed image such that when it fed into the network, the outputs of the two neurons labeled by dog and cat are 0.62 and 0.16 respectively. It indicates that the image is classified to a dog with a probability of 62%, to a cat with a probability of 16%. Therefore, it is classified to be a dog. All perturbed images with a 0.05 distance about the normal image are classified as dogs by the neural network. Then the neural network is robust. For more robustness, verification has been proposed and intensively investigated as a promising technique for certifying the robustness of neural networks. The problem of robustness verification is to check whether a given neural network is robust or not with respect to an input region. We consider an example of verifying a simple neural network. As shown in the figure, x1 and x2 are the input of the neural network. They all belong to -1 to 1. x3 is equal to sigma x plus x2. x4 is equal to sigma x1 minus x2. x5 is equal to x3 plus x4. x6 is equal to x3 minus x4. The verification problem is to prove that for any x1 and x2, it is always classified to the label of neuron x5. That is equivalent to proving that the output is x5 is always greater than the output of x6. Most efforts are focused on the ReLU networks that only use the simple piecewise ReLU activation function. Despite their wide adoptions in modern AI-enabled systems, another notable class of sigmoid-like activation functions, such as sigmoid and tige, have not attained much attention yet. Due to their nonlinearity, sigmoid-like activation functions are far more complex to be verified. A de facto solution is to over-approximate such functions by linear bands and to transform the verification problem into efficiently solvable linear programming problem. As shown in the figure, the original verification problem is the left of the figure, we just check whether x5 is greater than the x6. Due to sigma is nonlinear, we need to over-approximate such function by linear bounds. We can use two linear bound constraints to replace x3 and x4 as shown in the right of the figure. Finally, we just check whether the minimum of the x5 is greater than the maximum of the x6. So, the key of robustness verification is how to define the linear bounds to over-approximate the nonlinear activation functions. Considerable efforts have been devoted to finding the so-called tight approximations to achieve more precise verification results. Some researchers propose to measure the tightness of approximations using the enclosed area between the bound and the activation functions, as shown in the figure C. Another researchers adopted the tangent line that is parallel to the lower bound and its upper bound, as shown in the figure D. We performed empirical analysis of three state-of-the-art approximation approaches, namely deep search, VerNet, and robust verifier, on 20 sigmoid neural networks collected from the public benchmarks. The table shows the comparison results, where surprisingly, none of these approaches surpass the others for all the networks. Then we'll further analyze the layer-by-layer propagation in the verification process of the best two tools, VerNet and deep search. We track the computation of the intermediate intervals of the neurons on Henle layers during their layer-by-layer propagation. The figures from A to F show one 5-Henle layer network, named in1 on which VerNet computes a larger bound than deep search, while those from G to L show another 5-Henle layer network, named in2 on which deep search computes a larger bound than VerNet. The x-axis represents neurons on the corresponding layer, and the y-axis represents the differences of the interval lengths, lower bounds, and upper bounds of the intervals. The analysis results reveals that the intermediate intervals are statistically tighter than other tools, while 2 produces more precise verification results. Existing characterizations of tightness are individually heuristic and a presumption that a tight approximation gives rise to a more precise verification result. Unfortunately, the above empirical analysis show that this presumption does not always hold. It means that defining the tightness on each individual neuron is neither sufficient nor necessary for achieving tight approximations. That is because the tightness on neurons cannot guarantee that the output intervals of a neural network are always precise. However, the output intervals are the basis for judging whether a network is robust or not. Computing the tightest output intervals of a neural network is a complex non-convex optimization problem. We bypass the complexity from different perspectives via two efficient probability tightest approximations. Firstly, for one-handed layer networks, computing the tightest output intervals of neural network is a convex optimization problem. So we can leverage the gradient descent-based search algorithm to compute the network-wise tightest approximation. Then we can use the network-wise tightest approximation to compute the output intervals of a neural network. Finally, we can use the output intervals to check whether the network is robust or not. For the networks with 2 or more Henle layers, solving the optimization problem becomes impractical due to its non-convexity. The intractability lies in the accumulated constraints throughout the network. For any handy layer, the input intervals of the activation functions are constrained by the approximations to the activation functions for the previous handy layer. To our knowledge, no efficient algorithms or tools exist for such optimization problem. In such case, we propose computable neural-wise tightest approximations and identify the condition when all the weights in a neural network are non-negative. The neural-wise tightest approximations lead to being network-wise tightest. Our empirical analysis reveals an insight that preserving tighter intermediate intervals during layer-by-layer propagation usually produces a more precise result. In the same spirit, we heuristically define the tightness of an approximation to an individual activation function in terms of the overestimation caused by the approximation. Smaller overestimation implies a tighter approximation. Particularly, an approximation is the neural-wise tightest if it results in no overestimation of the output range of the activation function. For example, as shown in the figure A, x belongs to L to U. The output range of sigma x is sigma L to sigma U. The output range after approximation is also sigma L to sigma U. This means that this approximation does not introduce overestimation to the output of an individual neuron. So, the composition of all neural-wise tightest approximations is the network-wise tightest if the network is monotonous, namely width from the second layer to the last layer is non-negative. We first evaluate the performance of our gradient descent-based search algorithm on one-handy layer networks. The table shows the comparison results with other search tools. As shown in the table, our algorithm can compute a larger bounds with up to 116.66% improvement. Complete results are available in the paper. Regarding efficiency, the searching algorithm needs more time because it is in polynomial time, unlike the constant time approach for the non-negative models. Nevertheless, the gradient descent-based approach has been proven an efficient and practical solution to such a convex optimization problem. When the size of a network is reasonably small, such overhead is acceptable compared with the improvement of the verification results. Then we evaluate the performance of our neural-wise tightest approximation. The table shows the comparison results for 22 10H models with non-negative weights. Regarding the precision of verification results, our approach computes a more precise result than the competitors for all the models. In particular, our approach achieves up to 251.28% improvement. Regarding efficiency, all the approaches incur similar overhead as expected. They share the same complexity, namely 0.1 on each neuron. Despite the infeasibility of network-wise tightest approximations in the general case, we have explored the performance of our approximation method and the competitors on the networks of mixed weights. The table shows the verification results by each approach for 11 convolutional neural networks and 9 fully connected neural networks. First, the performance of each approach as compared with the others varies and different mixed weight models. Moreover, we observe that our approach performed surprisingly better than other approaches on all the experimented convolutional neural networks. The results evidence the network architecture is another factor influencing the verification. One possible reason is that a convolutional neural network is more possible to be monotonic. based on the fact that the neurons' weights on the same layer are constrained to be identical. Finally, we conclude some findings from this work. Activation functions should not be approximated with the same neural-wise tightness criterion. 2. Computing the network-wise tightest approximation is computationally expensive. 3. Network-wise monotonous is helpful to bypass the complexity barrier. While there still exist some problems, such as 1. Tight network-wise approximations are desired. 2. Application to train a robust neural network. Thanks for listening. Sorry we cannot attend ANC physically due to COVID-19. All the authors' information is listed here. Please feel free to contact us if you have any questions.